I'll walk you through what happened to photos between the sensor and a good-looking photo. Okay. Good. So we start at the beginning, and we will go through, and I try to give a brief overview of the processes and the type of machine learning we can do, and what I think is interesting or what problem remain to be solved along the way, and point to a few references. So the first step is demosaicing, and so demosaicing is what happened at the very, very beginning of the imaging pipeline in the camera. So we have a camera, there's some light that enters the lens. It goes inside, reach a sensor. That sensor has one measurement element for each pixel. That element measures only in intensity, so at this point there's no color. The way to get colors is to add what's called a Bayer pattern, meaning each sensing element has a red, green, or blue filter in front, so the intensity corresponds to that color at that location in the image. In addition, it's a normal physical sensor, so there is some noise, so we have this. Demosaicing is a step that the operations that go from this measurement where we only have one of the three, red, green, or blue at each pixel, to a complete RGB triplet at each pixel. And then more happen, and we'll discuss that later. So it's a heavily under constrained process because we go from one value per pixel to three values per pixel. So at this point, some of you may have heard about it, some may not know about it. And if you don't know about it, you may say, why are we talking about that? It works, right? We all have cameras in our pockets. I see many of you have them in the room. This operation happens all the time and delivers good-looking images, so why do we worry about that? And that's completely true. It mostly works. Otherwise, we would not have any of the digital cameras that we have today. But it doesn't work all the time. And if we look at the details, in some challenging cases, there are still problems that remain. So for instance, we see these kind of very thin features that are of the size of a pixel or less. They have this type of dot and flickering artifact, which is very unlikely that that t-shirt has this kind of dotted line along there. If we look at very complex pattern, for instance, these tree branches, we have some strange colors that happen. Or this thread there is very thin feature, is just so small that it doesn't appear not captured by the sensor because this demosaicing step blurred it out. And ripples and things like that are a problem. They tend to create wire pattern because of the interaction between the sensing grid and the pattern in the world. Wow. Okay, good. It looks like something that we can get a lot of data out there, right? There's a lot of photos there. So I don't think I need to tell this crowd how we can proceed. We just go out there, collect a lot of data, train a network, and that works, right? We all tried it. It seems to be something that we can really, as almost infinite amount of data and get it to work. And I was the same, so how hard can it be? Well, the problem is that when we did that, and we tried several architectures of network, the score got better. We did our PSNR went up. We first tried all the existing benchmarks, the PSNR went up a bit. But when we looked at it, these hard cases that I showed you, they were not getting any better. And there was some work by NVIDIA before deep learning called FlexISP was working. So we know it's possible to get better results. But we were not getting better results with deep learning. And so we started to look. The problem we had is that this problem I've shown you, there's a tiny portion of an image. And not all images have a problem like the vast majority of images just go fine. And when there's a problem, often it's a small portion of an image. So we're just getting better at doing blue skies. And that does not, it's already mostly there, so it didn't really matter to do, to improve on these easy cases. So the problem that we had is that hard cases are rare. So we proposed another way to proceed, which is a long version of the story that we have here. So we collected data, we train our network, and we get a baseline model. That the thing that I've shown you, it doesn't work very well. Like we match a set of the art, but no better than that. Then we use that and we implemented detectors for failure cases to find these hard cases I've shown you. And we went out there and mined more data, and I will show you what I mean by that. And for months we had machine running and searching for hard cases over the web. Then we had a new data set, and we trained again. And this is the result that we the one that we have. I have a lot of echo on my side. I don't know if it's good for you. Okay, so it's just me. So I'll go on.
No, it's not you.
There is echo, so maybe a bit farther away is better.
Yes.
Yes. Oh, awesome. Sorry about that. So, okay, we should have done that earlier. So, here let me show you what we have done. So that's ImageNet, like a big data set. So when we, you can tell by the look of the graph that we haven't been very soft. Like we went out there and mined data. Well, we mined a lot of data. Like we get out there and get 250 million photos out there. But as I told you, most of these photos are easy and not particularly challenging. So actually what we end up using is 2.5 million images that have challenging portions in them. So now we have this special case, this data set that's more representative of the problem we wanted to solve. And using that, we get results like we see here. So this is using the standard benchmark. And this is a collection of previous work. I put in I highlighted the 30 dB line. 30 dB or above in practice is usable. And 40 dB or above there's no point fighting anymore. That's my very grain of salt version of the story. So as you can tell here, this benchmark mostly saturated. This one case where we do well on this benchmark, we improve a bit, but we can question how significant that is. But then when we do the same experiment over the hard case data set that we built, we can see that it's a different story. At first we can see that a lot of techniques do well, and this is what I tell you, demosaiking works well enough to be useful, but it's not great. It's enough to be useful, there's room for improvement. We do significantly better, but I want to send the right message. We don't do perfect. We don't reach that 40 dB line where I think we can stop fighting there. So we show there's improvement, we show a way to do better, but we haven't fully solved the problem. So let me show you what it looks like in practice. So always a challenge with the projector, because sometimes the projector solves the problem for you. But I think in that case, you can see that example, that we produce better results there. And you can argue, unless you zoom, maybe it's not important, but there's a lot of professionals out there, and they care about this level of things. They buy cameras that are more expensive to get more pixels. They buy lenses that are sharper to get more precision. And we're talking about thousands of dollars or more of equipment to do that. So if we can solve it in software, it's a big deal there. So here's a case with Moiré pattern. Again, I think we can do, this one, the projector is nice. The colors are not as bad, but the program is very clear we have done better. Here, another case where we see that everything is so messed up between the branches that it's very hard to reconstruct and do this kind of checkerboard patterns that we addressed there. So, let me summarize what we have for this case. So, there's this kind of surprising conclusion. It's somehow, if the problem is too easy to solve, if the problem is too easy, then it can be hard to solve in some ways. So what we propose is actually to redefine the problem in a way that's actually challenging and that we have the hard cases to solve, so we can focus on the hard case. The general problem is kind of too easy to be tractable on there. We share the public data set there. You search our webpage and you'll find it. I'm sorry, I'll include it in the version of the slide I share. Now this is available in Lightroom. It's called Enhanced Detail. It's not exactly what I've shown you here. It's a bit less accurate because we need it to be faster, but it's mostly what I've shown you here. There's a lot of nice work that has been done in there that use the same thing but also optimize the bio patterns that we see at the beginning that specialize on low light imaging. I strongly encourage you to check this out. A lot of things I have not described today is that how we deal with noise, how we build these detectors, But I think the main idea here to remember is that this is a hard case, but the hard cases are the long tail of the distribution, and unless we build a data set for that long tail, it's hard to solve. So I'd like to move on to the next step. Now we have a color image, so we need to make it look better. And the motivation for that is here's a picture that comes out of the sensor. It's colors, nothing bad there. It's not that great. Like the projector makes it look a bit better than it is. It lacks a bit punch, to contrast, a bit luminance. Here's what a photographer would do before doing any kind of stylization. Just fix exposure, fix the contrast, making it look at a stage where you see the potential of the picture before you decide what to do. This is a step that photographers do all the time. This is the first thing, is that straight off the camera we get values and an image that tends to be a bit bland. We fix exposure and contrast, and then we work from there. So we proposed a way to automate that. That was pre-deep learning, and I'll show you what we have done, and I explain why I show the pre-deep learning version at the end. We use Gaussian processes regression there. So if you're not familiar with Gaussian process regression, what it does, the intuition is fairly simple. We have a reference of 5,000 photos that have been retouched by hand. The algorithm essentially can be interpreted as finding the training samples that are the most related to that photo, combining the labels, meaning the adjustment made by the photographers, take basically an average of that, infer an adjustment, apply that adjustment to the photos as we see it here. So here let's compare what we have to the ground truth version. Of course, the photographers, the ground truth was not part of the training set. There, it's not exactly the same, but it's close enough. And this is really average performance in terms of error. We're exactly at the mean. This image has been selected for that purpose to show you that we can get close to the photographers within small differences. And it works on all sorts of images, so here completely different content. I have to disclose this is the better than average performance that we see here. There. So the first thing that this works well, as it's in Photoshop. When you press Auto, that's what happened. But it raises a few questions. How do we do that with deep learning? And I think it's not an easy question. It's a Gaussian processes. They can work from a few hundred of photos only. And that's not obvious how to do that with neural networks that tend to thousands or if not millions of data points. And the reason why we like to work with a few hundred of images is that when we ask experts to give us ground truth data, 5,000 photos took 3 months of work. So we're not going to get millions of data from experts in general. So I think being able to work at that level is useful. Then Gaussian processes can be set up in a way that if we show an image never seen before, like something really different, for instance, an astronomy picture, it will revert to the mean of the data set. And that's good. It's not taking any risk. It's a very safe and predictable behavior. It's not, I'm sure we can do the same thing with deep learning. It doesn't seem straightforward, but it's something to keep in mind. Also, we can fairly easily do transfer learning with Gaussian processes. We can learn from the user directly. If they don't really like that version of the flower, but they like something a bit darker, we can, within 1 or 2 examples, we can learn that and reproduce it after. So it's really like few-shot or one-shot learning is straightforward. With deep learning, it's doable. There's more and more evidence we can do that, but it takes some work. So looking at the other side, like for deep learning, we have to deal with data scarcity. We don't have that much data when we work with the expert. And there have been a couple of items that I mentioned. I've been involved with work from people in Hong Kong where we work as a patch level. So that's one way to turn thousands of images into like millions of patches. And now we can train. So this work is nice, it's accurate, we show good performance, we show that we can cope with different styles. The problem is that it's an unconventional model. It's hard to reduce this to a number of sliders or curves that people are used to doing, the professional are used to work with. So it's not obvious how to put that to the traditional photograph editing pipeline. Recently, last year, there is Yomi who showed this work on called exposure that with reinforcement learning and GANs show amazing results. It has the parametric models that fit very well existing pipeline. It supports stylization, like it can do basic adjustment and also more stylized adjustments, which is great. It's a very complex system at this point, and the accuracy, if the goal is to reproduce a professional adjustment, it doesn't match ground truth very well. But I think it's a very interesting direction, and we need to explore that more. So let me move on from there. Now we have the photo, we fix the basic things. We'd like to express some style, something more, not just making it look good on average. So we're going to look at style transfer. And here, the inspiration of the work I'm going to present is the work by Leon Gattis that has shown great result on paintings.
To class labels, which was a lot more than the 20 labels we used in the Cityscapes dataset. The style of the generated image is controllable. You can steal styles from the style image, and it achieves all this using a fewer number of parameters. So how did we do this? Here's our motivation. A standard deep network consists of convolution followed by normalization. We know that normalization yields nice properties such as smoother gradient flow or maybe invariance to input scaling, but we found that doing so with input semantic map gives sometimes too much invariance, sometimes even losing semantic information. So here's a little thought experiments we can do. Let's say the input semantic map was just flat uniform label, for example 100% grass. Then after convolution, we're going to get activation, and at each channel, we're going to have uniform neural response at each channel. Then after normalization, because we subtract the activations by the mean of the activations, we're just going to get 0. And this is true no matter what kind of class label we're going to use. And this was indeed true in case of Pixelpix HD. If we input flat label, no matter which class label we use, we always end up with just a gray image, which just means 0 everywhere. So here's our solution. We propose to actually just provide this semantic information after every normalization. And this is indeed kind of what we did. And as a result, using our model, you can see that even if we input a uniform flat label, we are going to get the correct texture for each class label. So this is what we did. We extended the idea of batch normalization. I think you probably all know that batch norm consists of 2 parts. First is the normalization parts that computes the mean and variance and make the output distribution zero-centered and unit variance. And the second part is the learned affine transformation part that allows more flexibility to batch normalization. And we call this part denormalization because after the second part, the distribution is not normalized anymore. And the key to our approach is we made this denormalization part conditioned on the semantic map. So in more detail, given semantic map, we pass it through a couple of convolutional layers to produce tensors of gamma and beta, which are going to be the parameters of our affine transformation. Then given the normalized statistics, we do element-wise multiplication addition. It's basically applying gamma and beta to the normalized statistics. It's closely related to many previous works. One of them is class conditional batch normalization, which was actively used in image generation on ImageNet dataset using GAN, including spectral normalization GAN, self-attention GAN, and also big GAN. Here, the affine parameters, affine transform parameters, are conditioned on the one-hot class vector. But in this case, it's class conditional, so you basically have the same class vector for all pixels of the generated image. So the affine transformation parameters are actually spatially uniform. Conditional normalization can also be used in adaptive instance normalization for fast style transfer. What you do in this case is, if you just replace the affine parameters by the ones produced by the style image, then you basically get the output image rendered in the style of the style image. Our method is also closely related to the spatial feature transform last year in CVPR. It uses conditional normalization for the task of super resolution, but in this case, the affine transformation parameters are conditioned on the predicted class label of each pixel. So here we have the spade module. It's designed to replace the batch normalization of any deep network. So for example, the residual block we're going to have now will look like this. So instead of batch norm, ReLU, convolution, we are going to have spade, ReLU, and convolution. And at each spade module, we're going to have the input semantic map as its own input to its layer. Then now we can use the same architecture that's used in many popular GAN generator architecture, which was residual ResNet-based architecture. So you start from random noise, and then you gradually upsample the image, but at each ResNet block, we're going to feed in the semantic map to provide the semantic information. And this differs from the architecture of Pixupix HD, which was state-of-the-art previously, which has encoder part that processes the input semantic map and decoder part that produces a photorealistic image. Now, in terms of this architecture, we have only the decoder part of Pixupix HD, and this saves a number of parameters of the generator architecture. We also have GAN loss, like Pixupix HD, to enhance the visual realism of the output image. We also have other tricks that we used, and it confirms the findings of other GAN papers. For example, we used a larger batch size, and we confirmed that it actually helps the output quality of the generated images. We go from 8 in Pixupix HD to 32 in our case. We also used synchronized batch normalization, which synchronized the statistics of each GPU. We also used spectral normalization with hinge loss, and it helped our training in terms of both the stability and also the final output quality. So here are the results. Given this input semantic map, this is the result of CRN and Pixupix HD. I think Pixupix HD creates these artifacts because we have large flat label. And ours generate the correct texture even for the background. You can see that CocoStuff dataset is more diverse. It contains animals, people playing sports, and interior and food pictures, and so on. And this is the results on the outdoor subset of 8020K. Now that we sufficiently reduced the size of the dataset, we can actually compare with the result of semi-parametric image synthesis. And you can see that on the top left, the result of SIMS looks very realistic because it steals the real image patches from the training set. But once you compare it with the input semantic map, you can see that it's actually not perfectly observing or respecting the input semantic mask. Here are some more results.